Yeah, can you guys see the screen?
Yes.
Yes, the screen
Oh,
is.
okay, good. ठीक है. Um, okay, good evening and welcome to the week 11 live session for your Intro to Machine Learning course. We'll do the assignment 10 questions and then we'll discuss some things about neural networks clustering and K-means plus plus in case it hasn't been discussed before. Okay. So week 10 assignment was this. Um, yeah. So the first question here you have is, suppose you have a cluster of data points. There are some points here mentioned. Find the data point X which has the highest average L2 distance. So basically, I think the idea is that you just find from each point the distance to all the other points, and then you take the average over them. We should ideally get, I guess, this minus two as your answer. All right. Then which is the first statement is not either or not true about K-means clustering. Obviously, it's what it is. There is K-means is a hard clustering technique, which is exactly opposite of what is written here, right? So clusters do not overlap in K-means clustering. Overlapping clusters basically means it's a soft clustering technique, right? So a point can belong to more than one cluster, whereas here in K-means we don't allow that, right? So we'll go through the programming part of it. All right. Um, yeah. So question about K-means. So see, first thing is first. Said that we need to use this sklearn version 1.0.2. So luckily, Google Colab by default gives us this one. Okay, that is your this version that you want. Then we have seed equal to 42. They mentioned to use 42c. That's fine. And then if you see always better to set this random seed to whatever seed they're given using this code here, right? And then you have load digits xy equal to true. I saw one question about this, that shouldn't be split into training and testing and stuff. See, in at least in case of in case of clustering also you should do training, testing and all of that. But the idea is that it's not mentioned in the question, so don't do anything extra that you need to that might screw up your values, because this is programming assignment, and that too only results are matched, not the code. So always better to follow exactly what has been mentioned in the question. All right. And x, if you see, it's like a 1797 number of samples and 64 features of this particular MNIST image. All right. And then you have the y shape is basically going to tell you what class it belongs to. So for example, let's say if you were to view this, so you have like 0 to 9 sort of numbers. So basically you have 10 classes, so 0 to 9 are your class labels for each of them. And what has been asked, they've asked basically that can you run k-means on this 10 using 10 as your number of clusters, and see what is the prediction that you get. All right. So basically if you see here, so you have your in clusters, you have your random state is equal to seed, you fit the k-means on this. So this basically learns your 10 clusters on this data set, in this dimension 64 dimensional data set. And this is your labels dot labels tells you exactly which cluster number was this so and so point assigned to. So this k-means dot labels labels or shape is going to be again like a y dot shape, because it's going to be for each sample which cluster number was assigned to this particular sample, right? And what they've asked is they've asked label the prediction class for all the points in a cluster as a majority true label. Okay, so what that means basically is yeah, so let's say you have you know, the true labels are like this, for example, let's say. Okay, but what ended up happening, let's say, is that these clusters became, I mean, these points became one cluster, and these points became another cluster. Okay. Okay, so what you will do is you will say now that all these points are actually cross only. Okay, this is now the assigned label for this is cross, the assigned label for this is circle. Okay, and then so now, so we basically have a prediction and a truth value from this particular sort of understanding, right? So basically all these points have the same predicted and the true value. This point has a different predicted and true value, and so on. So therefore you can calculate something called as accuracy, because for accuracy you need both the true and the predictions, right? Predictions and true labels you need. This true is basically whatever the actual class label is, and here this predicted is the majority label of the class to which this most of the points in this cluster belong to. Yeah, so we'll do that approach here. So that is, we say, okay, prediction is first we take an empty array, and then for each cluster that is in range of 10 for 10 clusters, we look at what all points will belong to those cluster. We find out the maximum label of the points in the cluster, and then assign to that particular class the particular points to that class. Okay, so this approach will give you that, and then accuracy is just your equality of mean, right? So you get 0.79 as your answer. All right. The second thing is about the rand index. So rand index, you can either code it up, or Scikit-learn already has a method called rand score, so you can use that to understand what rand score on what your score should be. So that's your 0.933, which is what is the answer here. Yeah, so I did see a lot of questions regarding this rand index and accuracy thing here. So this was actually meant as a question to confuse you all. So here the idea is that, see, though you can always write this sort of an equation for the accuracy and the the rand index, the idea is not that. The idea is that you want to know how are they related. uh, the thing is, there is no relation as such, because of the fact that rand index works on the pair of elements, and accuracy is something different altogether, right? So whatever you get a relation to be, all of them, they're all spurious. They just exist because of the fact that these two are numbers. So you can always write a is equal to b into c, because a and c are numbers. Okay, so the right answer is none of the above. Okay, fine. So any questions till now? No.
Okay.
Sorry. No. Okay, fine. Yeah. Okay. Okay, then the birch question that was there. So similar sort of an idea. You'll again do your take 10 clusters of under this birch algorithm. So I'm not sure exactly what birch algorithm is, but then I guess that's the thing about not knowing. So here so you can get your predictions in this, again, same idea, and then use your rand score metric to understand what your rand score would be. So this turns out to be your 0.963, which is your answer in here in the birds question. And then you have your db scan question. So again, same thing. So the idea in db scan was that you first want to apply db scan on the raw data, that's your MNIST data set that you have, and the second thing is you also want to apply it on the PCA features that you get, PCA with two components only. So PCA features in a sense, basically you take first two components, and then you project your data back into that space, right? So therefore your 64 dimensional data becomes now 2-dimensional data, and then you apply db scan on that. Okay, so first is where we apply db scan on the actual data, that is x here, and you can see so labels may if it is -1, it's taken as a outlier. So here DB is kind of saying that everything is outlier. Out of 1797 samples, all are outliers. So basically here it means that with this particular sort of the distance measure that you have, min samples equal to 5 and EPS equals to 0.5, you are not able to find any core points or these non-core points and so on. So therefore you end up having all of them as outliers. The second thing is you need to learn your PCA. So PCA n components equal to 2 dot fic of x will learn the PCA algorithm. So basically so now you have you know which two components to project your data on. X hat so your transform of x will project your data from x space to your x hat space. That's a PC space, and you can check the space dimension here. It's going to be 1797 comma 2, right? And then you can do your DB scan on that. You get your number of outliers to be 1742 sort of a thing. Okay, fine. So any doubts until now? Anything here? No. Okay. Fine. So we'll move ahead with the other part of the lecture today, session today. So yeah. So there were some questions which seemed like good to cover if in case you want to discuss. So we have a similarity matrix here. This P1, P2 are basically all the points, right? And each of these value tells you how similar these points are. So just remember always that when you say similarity, it's always proportional to 1 by distance sort of a thing, right? In a sense, like these two are oppositely related, okay, negatively related in some sense, distance.
Raj, excuse me, Raj.
Yeah.
So I had a small, very general question. So there were many instances when professor was speaking that which particular metric to use. Somebody was preferring Mahalanobis distance, somebody was saying Euclidean distance. Is there any cookbook approach to this choosing of distances, or is it very specific, as in case-to-case basis we'll have to take those metrics?
Okay, so you're saying which is a good distance measure to check
Yeah,
different points?
means is there any general guidelines for choosing metrics in these kinds of clustering problems?
At least as far as I know, there isn't. So people try different metrics and see what works for them, but I mean, I did read somewhere that using Euclidean for very high dimension spaces is not good, because of
Yes,
the things
yes, exactly.
yeah, your square root and all of that will just start going bad.
Yes, because the sparsity thing, right? Because
Sparsity,
the space is mostly flat and mostly empty in high
mostly empty.
dimensional spaces.
Correct. So because of that, but then exactly what should be the right metric to use? I don't think there's a right answer there, but guidelines they might be there, but I'm not aware of them. Yeah.
Okay, fine.
Yeah.
No issues.
So if you want, I can try and see in case there's something we can
Yeah,
see probably
something to read up, because it
lecture.
sounds a little very vague to me. I did not get to read something. So if you can give a pointer, it will be helpful probably.
Sure. Okay. So distance metrics, is it? Fine.
Yeah, the selection of distance metrics.
Got it. Okay. I'll see what references exist, etc., and then we can probably have a discussion also next live session. Okay, good.
Okay, thank you.
Fine. Yeah. Okay. Yeah. So we have the 6 points present here, and we have a similarity matrix which is given here. So if you were to use a single linkage sort of an approach to your clustering, so basically you can see that P2 and P3 will get clustered first because you have 0.95 as your maximum least distance in some sense. Then you have is P5 and P6 because you have they have your thing to be 0.85, the next maximum. Then when you compare all the remaining points and you try to find out which is the best one, the idea is, in single linkage is that now these two are combined. You look at the point with any of these points in this cluster, right? So you look at P4 with P5. Okay, P4 with P5 is 0.8, P4 with P6 is 0.65. Okay, so the distance between P4 and this cluster is now chosen to be 0.8 because you look at the maximum similarity or basically the least possible distance. So hence this value comes up, and therefore P4 and P5 6, these are merged. And then you go on similarly, you can see P2 P3 with this cluster. So P2 and P3, 0.95, and then 0.75, right? So because all the remaining are 0.7, 0.65, 0.4 low values, so you can see 0.75 here. So this merges your P3, this cluster, P2 P3, and this cluster P4 P5 P6, that gets clustered here, and remaining point is only P1 that gets clustered. Okay, so similar idea with complete linkage. If I'm not wrong, the idea here is that you look at the average distance between your different clusters, but but for this to work, you would need like actual distance values but not similarity matrix. So unsure, like how distance and similarity, how do they interact when you say averages in condition, right? So anyway, so for single linkage, this would be the clustering hierarchy that would come up. So we had this one question in your practice questions which said, which among K-means, single link and complete link and DB scan will perform well on this data? So any ideas as to what would work in this and why so? Any ideas? Uh, you guys can see the image though, right?
The colors are nearly indistinguishable. It's very light. Yes.
Or is it? One second.
The contrast is screwed up.
The okay.
Yeah.
Is this
That is a
better?
little better, I think.
Okay, yeah. Okay, so we have this question. So all the points here are red. That's the thing. These are all red. This is all green, and these are all are blue, right? So these are actual labels in some sense, in the series that we saw with MNIST, right? So if you were to use any of these algorithms, which would you think would perform well in this sort of sort of a data set?
For the red and green points, DB scan would perform well because the density is, greater in those areas.
Mm-hmm.
But I'm not sure. Like if we want to just cluster, so if we cluster red and green, the blue is automatically, classified.
Uh-huh.
So I think DB scan would work.
But one doubt. So when you said DB scan, you're looking at density and seeing that okay, these two are more dense and so on. But how would you just cluster these points only? Like you can't just say choose these points first, cluster them, and then remaining are the other ones, right?
Yes.
Sorry.
Need to think about that. Yeah.
Oh, okay.
Need to think about.
Okay.
Treating those blue points as an outlier.
Treating them as outliers. Okay. But you can't really say all outliers are one cluster though. No, I mean that would be pushing it a bit. The idea of
Okay.
outliers being one clusters, because for example I could have a data set data like this, right? Though where I have all points like this and these two are outliers, so telling them as as one cluster could not be right in many senses actually.
Okay.
So I just go for complete link hierarchical.
Completely hierarchical. Okay.
That sounds reasonable to me because we are building up the clusters one by one.
Okay. But
The
okay, fine.
closely knit points we are taking up as one cluster, and another in the periphery we are taking at another cluster, then probably merging them at a higher level. Sort of that.
Okay. 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 But no takers for K-means, is it? How many of you think K-means could be the right approach here? No one. Okay. Fine. Yeah. So K-means may not work very well because the idea of K-means is that you need to assume, things like, for example, spherical clusters and similar, radius and all of that. We see very clearly that these points as such don't have a same sort of a spherical nature as compared to these points. My idea was DB scan because of this reason that your single link and complete link hierarchical, they can also work. You might want to put sort of a like a threshold. If you put, okay, a stop when I get three clusters, you might still get these three clusters in that way. But DB scan, it's like, it's more of, the number of clusters depends upon your parameters that you choose, right? Your EPS and your minimum points connection and all of that, right? So I was thinking that DB scan could work because of the fact that so all of these points as such, right, all of these points as such could become core points under some value of EPS, right? So I could say, for example, if I keep like 4 or 2 or 3 or so on, and like keep the distance measure to a bit of a minimum. So what will happen, what will end up happening is it might start going through all of these points one by one and not even touch these points. So hopefully it might do a bit better compared to the remaining three methods, right? The answer is DB scan, but the rationale is probably that DB scan doesn't depend on, like, it doesn't make any sort of assumptions on the shape of the clusters. Rather, it is all about whether can you find points close enough to it or not, and in any shape. And hence, I mean, so I was hoping that all of these can end up becoming one cluster because of the idea of keeping your the EPS and the min points to be a bit low. You might be able to cover all of these points under one cluster. Yeah.
Raj,
Yeah.
can GMM work on this type of cluster?
GMM also won't work because the fact that, see, GMM, what it will say is, it needs like, okay, so I will just put it here.
And it also doesn't have any restriction on the shape, right?
Correct, but it needs all the points to be closer together though, right? For example, now if you're hoping that you'll get one Gaussian here, one Gaussian here, the remaining points cannot become one Gaussian, right? They have a different shape altogether. See, in GMM, what is the idea? The Gaussian mixture model, the idea is that it's a mixture of Gaussians. So after all your the clusters should be in some form of a Gaussian. The good thing about that compared to KMeans is that it doesn't make any assumptions. It can handle different clusters having different shapes, right? But we should be able to express them as Gaussians of some format, right?
I
So, for
mean,
example,
if that's a 5 cluster problem, so a GM work, right? For instance, the leftmost part would be considered under